Okay. Okay, so okay, good morning. Let's start the lecture, and let's continue from previous lecture. Okay, this is a quick review of what we did from previous lecture. So previous lecture we talked about impulse sampling, zero order hold, and open loop pulse transfer function. So this one here is basically a sampler, but mathematically we use a impulse sampling model for this one here. And if you recall that, that's essentially what we call it a Dirac-Kuhn kind of model, right? Yeah. And what's given to the Dirac-Kuhn is a continuous signal x of t. It's a time signal, and coming out of it, it's still time signal, okay? But it's a discontinuous one, so we call it x star of t. Okay. Practically, what's come out of the sample, of course, is just a sequence of numbers, right? Yeah. So, but mathematically, this is just a start signal here. And this one given to a transfer function block h of s. Okay, so h of s could be representing several things. You know, it could contain a zero order hold, basically a zero order hold plus another block at here, and then its output here, right? So what you need to know is anything after the impulse sampler, it's the one with the starred one, right? The one starred. Okay. The open loop or the pulse transfer function for this simple block, okay, it's h of z equal to y of z over x of z that we prove from that we show from previous lecture, okay, from lecture. So where this is from, it's basically if you recall that this x star of s, or you can use any symbol right here, okay, when you replace the s, okay, with 1 over t log z, you get the corresponding, okay, x of z, okay, x of z. Yeah. So technically speaking, where this h of z from? This h of z coming from this h star of s, right? Star of s. So you need to find the ratio between y star of s over x star of s, then find h star of s. Then the h star of s give you this h of z by doing this substitution here, right? Yeah. Essentially, there's a couple of things that here. Basically, I think you need to be careful here is, so in order to obtain the h of z at here, you look at this one here, h of z. Okay, so you can obtain by doing this division of the ratio. Basically, you can try to obtain y of z first, h of z. So in other words, so to, okay, let me just write down it. To get h of z, you can either do what? So get y of z and x of z, and then h of z equal to the ratio, right? So that's one way of doing it. Okay. But this is not the very efficient way, because sometimes it's not that easy to get y of z, x of z just based on the signal, right? So the other way of doing this is it's this, from h star of s to h of z. Okay, to h of z. Okay, and for this particular approach here, so what we usually write is, okay, we write as this. So h of z, okay, equal, okay, this. Okay, in later I'll show you a formula. So how do we easily obtain this h star of s from h of s? Okay, so from h of s we can easily obtain an h star of s. All right, yeah. So remember this one here. We'll have a formula for this one here. Okay. But the pulse transfer function in here, okay, basically h of z, essentially can be written as this one here, z h of s. But when you write this one here, you gotta remember one thing, okay? You gotta remember one thing. So when basically we say, okay, what is that transform H over Z? So what this one implies is, okay, so it implies there is a impulse sampler. Okay, there is an impulse sampler, okay, in front of this H of S. Okay, when you do this here, the meaning or the physical meaning behind this process or behind this operation here is there is an impulse sampler in front of H of S, right? So just like this case, there is an impulse sampler in front of this guy here. Okay, yeah, that's how you can do this step here, right? Yeah. And we'll talk a little bit this summer after. I'll give you one example. Okay, then we'll talk about and summarize a little bit here. Okay, so let's look at an example here. Okay, so example. So this example we'll look at pulse transfer function of a very simple open loop system. But this simple example right here, okay, it's sort of foundation. It's very important. So you're gonna probably make use of this little block in many situations. So here is a zero order hold at it here, and then here's a plant. Okay. Okay, so that's this block here. Okay, that's this. Yeah. So what we want to obtain or calculate the pulse transfer function for this block here. So zero order hold and the plant. Essentially, it's like there's no controller here. That's just whatever this manual input discretized, give it to zero hold, and then feed it to the plant here. Right? Yeah. So if I compare this block, okay, with this block in general here, but there's one box to here, so there are two boxes here, okay, but these two boxes, so by observing it, there's no sampler between, so basically these two things here is that one block over there, right? So over there, okay. Yeah. So let's essentially saying is let's let this H of S equal to this block multiplied by this block. Okay, so that's our H of S. And if we rewrite it just slightly different, okay, like this. Yeah. So actually you can see the effect of this zero order hold here just by looking at this superficial operation here. So when you just have a plant, you know, that's just a system, right? That's G of S. But now when you have a zero order hold here, see what happens is zero order hold contains a what? Contains a S on the numerator, on the denominator. So basically that meaning there is a pole of S equal to 0, right? S equal to 0 here. So when you add this block here, multiply this one here, so now these two blocks together, you can consider this G of S also has a numerator divided by denominator, right? So the zero order hold basically add a what? Add a pole of S equal to 0 to your system. So it changes the dynamics slightly, alright? Yeah. And the other thing is, the zero order hold has a e to the power negative ts here, right? Has this guy here. So when you have a e to the power negative ts, physically what does that mean? Delay, right? So basically the zero order hold also adds delay to the system here. When you learn continuous control system, so when you see a transfer function, let's say when you see a transfer function numerator over a denominator, then multiplied by a certain kind of e to the power a certain kind of s here, right? So we know that the system has delay, and there's another name for this kind of system. This kind of system is called, I wonder if you learn this in here. It's called what? It's also called non-minimum phase system. You remember that? Yeah? Oh, no? Yeah, okay. So this kind of system is also a non-minimum kind of system. So when you have this kind of system, and when you look at the step response of this kind of non-minimum kind of system, so you can actually distinguish that kind of easily. Actually, probably that's not the case here. Anyway, so by looking at this one here, the point here is you can see the effect, okay, of this zero-order hold, okay, imposed on the original system. All right, yeah. So what we want to do is we want to obtain the Z transform, the pulse transfer function, right? So pulse transfer function, according to what we have here, pulse transfer function, because there's an impulse sampler here, so I'm going to just trying to get the Z transform of this H of S. Okay, so the PTF is H of Z, okay, equal to Z, okay, H of S. Okay, yeah, so that's what we're going to try to obtain. Okay, so is zero-order hold, Z transform of this one here, which is Z transform this. So let's put that into this bracket here. And this G of S over S, let's temporarily let it call it G1 of S. Okay, just temporary. Okay, so now let's see what will be the Z transform of this thing here in the block here. Okay, and if you have your Z transform table, right? Remember I said there are a couple of columns here, right? First column is S block, S function. Second block is a T function. So technically speaking, okay, so when you write the Z transform of the S function, it's equivalent to say a Z transform of the corresponding time function. Okay, yeah. So for the one in the block here, it's G1 of S ETS G1 of S. Okay, is this. So let's just assume that the the time function for G1 of S, okay, let's just say that it is G1 of T, right? Yeah, so a time function, we don't know what the G of S is, so I'm not writing any specifically the time function here. But let's just say that G1 of T is the time function, or the inverse Laplace transform of G1 of S, right? And the second one here, when you have e to the power negative Ts multiplied by this G1 of S, as we said, it's a delay, right? It's a delay. So this is basically delay by how much? By this T here. So then the corresponding time function for this one here will be T minus capital T. Okay. Basically, the inverse Laplace transform, okay, inverse Laplace transform of this one is G1 of T minus capital T. Okay. So that's the time function here, right? Time function. And then the Z transform for this and that, then the process is you're going to discretize that. You sample this or sample that, and you take the Z transform, right? Take the Z transform. So suppose that if you do that process, you get, okay, this G1 of Z corresponding to this G1 of T. And here you have a delay, right? Here you have a delay T minus the capital T, the one sampling time. So if you recall that one of the property, this is a continuous one. After sampling, it's KT minus T, right? KT minus T. And this is basically G1 K minus 1 capital T, like this. That makes sense, right? Yeah. So this is one basically this is a step, this is a delay in time domain, a delay of a sampling time T. And here is a delay of what? In terms of the sequence number, it's a delay of one step. Yeah, this is the delay of one step. So when you look at your Z transform table, there's the property when dealing with this one step delay. So if the Z transform G1 of T is G1 of Z, then the Z transform of this is simply just multiplied by Z to the power of -1, right? So Z to the power of -1 represents one step delay, right? One step delay, okay? So this is the Z transform of this one here, right? This one here. Okay, so now you can rewrite this slightly. This is 1 minus Z to the -1 and G1 of Z. Okay, G1 of Z. So what is G1 of Z, right? So we see that the G1 of Z is basically the Z transform of G1 of S. And what is G1 of S? G1 of S is what we define temporarily. That's G1, G of S over S. Okay, G of S over S. So overall, okay, now I can obtain I can rewrite my H of Z now. So H of Z equal to this guy here, and that's Z minus 1 over Z, and multiplied by G1 of S. Z, G1 of Z is this quantity here, so Z G of S over S. That's it. Okay, that's the pulse transfer function. Okay, for for this block here, for this block. Okay, this block. So if we have the planned Laplace transfer function G of S, so then we can proceed to get a specific at Z function, right? And we'll get a numerator divided by denominator, that kind of expression. Okay, yeah. So what I need you to remember out of this simple example is, okay, because we're dealing with a digital control system, and many times the first step you do is you have to discretize your plant. And one way of discretize the plant, okay, is to have a fictitious or to make a block, to put a block in front of your plant, zero order block, zero order hole in front of plant. So then your plant will be discretized and as this one here. So instead of using S now, right, instead of using S, you have the corresponding Z transfer function, which is this. Okay, yeah. So that's the conclusion you need to remember here. Okay, so when you have a zero order hole in front of a plant, the corresponding pulse transfer function or Z transfer function is this multiplied by this. Okay, yeah. Good. So, do I have one example here? Yeah, so actually we do have one example here. Let's just see, let's see here, if G of S, okay, equal to 1 over S plus 1, okay, then let's see what will be the H of Z. So H of Z will be Z minus 1 over Z, Z 1 over S, S plus 1. Okay, like this. Yeah. So it's the Z transform of this one here. So I'm not gonna do it, but let's just see your Z transform table, right? From your table, if you have a similar ones there. Do we have a? Yeah, we do, right? Yeah. So basically, you can save your time instead of going through the process. You can directly or grab it from the table. Okay, so where is it? This guy here, right? This guy. Okay, so the A value here is 1. Okay, A value is 1, and this is the corresponding Z transform. Okay. Yeah. So let's write that down. Okay, So this Z transfer according to the table is 1 minus e to the power capital T Z minus 1 Z minus e negative t. Okay, yeah. So it just happened that we can cancel something in here. Cancel this, and we can cancel this, right? Yeah. And we are left with we're left with this one here. Okay. Yeah. So that's this pulse transfer function. Okay. Yeah. So in previous lecture, I mentioned another thing. Okay, you have a pulse transfer function. In Laplace, you have a Laplace transfer function. So in continuous time system, the inverse of the Laplace transfer function give us the so-called what? The inverse of the transfer function, S function. Give the time, but yeah, but if this one represents the transfer function, then the inverse will give us impulse response, right? Yeah. So this is a Z transform, then the inverse of this Z transfer function is supposed to give us also the impulse response. Okay, but it's a different idea though, right? In continuous time domain, impulse response is when you give the direct delta into the system. But when it's discrete time system, it's the response when the input is the Kronecker delta signal. Okay, yeah. So in other words, if I take inverse Z transform of this one, I'm supposed to get the impulse response, right? Yeah. So I'm supposed to get impulse response if I take the inverse of this, okay, h of z. Then the next question is, maybe the question we'll ask is, would you have a stable impulse response or not for this system, right? Yeah. So how do we know that? And that's the question we'll deal that in more detail later, but I think I mentioned slightly here. In order to do that, just like the continuous time system, you look at the pose of S, right? Same thing here. You're going to look at the pose of this denominator here too. Okay. So the location of the pose determines the stability of the system. And in this particular case, okay, and you can memorize the conclusion for now. For Z transfer function, when the poles of Z are in the unit circle, you have a stable system. So then for this one here, there's only one pole, and the value of that pole is this guy here, right? It's this. So the question is, if this is in the unit circle, then you're stable, right? Yeah. But actually, t is a sampling time, so really doesn't matter what sampling time you give it here, right? So this e to the power of negative t. So t is always greater than 0, right? T is always greater than 0. So this value is actually always less than 1. Okay, less than 1. So you have a stable system here, though, right? Yeah. However, okay, you can see the effect of the sampling time, though, right? If you give a different t value, so this value will change, right? This value will change. Okay, yeah. So basically, that's a question of the effect of the location of the pole to the relationship to how fast the response is going to be, right? So I think we'll deal with that later here. But for the time being, I can tell you is if the sampling time is small. So the sampling time is small, meaning you have a fast sampling frequency, right? Fast sampling frequency. If t is small, then e to the power of very negative, very small number means this is going to be close to 1, right? It's going to be close to 1. Okay? Yeah. So if t is small, it's going to be close to 1. If t is big, it's going to be close to 0. So closing to 0, okay, give us a faster response. Okay? So basically when the pole is close to 0, okay, so when pole is close to 0, okay, yeah, you have a faster response. Okay? Yeah. So actually, I shouldn't say faster response. I should say a faster decay. Okay, so basically decays faster. Okay, it decays faster, right? It's like this, right? You know, you compare to 0.5 to the power k and 0.2 to the power k. So which one decays faster? This guy here, right? Yeah, it goes back to 0 faster. That makes sense, right? Yeah. And this is closer to the 0 there. Okay? Yeah. So in this particular case, basically, higher sampling time t give us a faster decay. Okay? Yeah. So it's a little bit non-traditional. Yeah. Okay. Yeah. Okay. So that concludes with this example here. Okay, so I'll show you some MATLAB simulations. How would you conduct these kind of simple simulations using common MATLAB functions? Okay, yeah. So from this stage on, and many things you can basically skip the hand calculation. You can use MATLAB, but my requirement is a lot of things. I need you to hand calculate the simple cases. Okay, then verify that using MATLAB. Okay, so that's what I want you to do at this early stage. All right, but later when you do project, when you do simulation, so you can do everything in the in MATLAB environment. Okay, yeah. So to summarize, okay. Yeah. Here is what what I want you to establish the concept here. Okay, so the whole idea is you have the S block. So this H block can give us this S H star of S, and then this H star of S can give us this H of Z. Okay, or another shortcut is you can just simply try to get from H of S to H of Z by doing this. However, okay, you gotta be careful when you do this. You gotta know that thing that I was talking about here. When you do this, meaning you have an impulse sampler in front of this block there. All right? Yeah. So when you do this, just remember there is impulse sampler. Okay. In front. Okay. Yeah. Now the whole question, if you do from here to here, then the key step is from here to here, right? So how do I obtain H of S to H star of S? Here's a formula, and I need you to memorize without the proof over here. It's called the residual formula. So one of the exercise I'll give you today is to exercise how do you obtain H of Z by using this approach here. First from here to here, then from here to here, right? Yeah. If you go this route at here, okay, you need to use the so-called residual formula to obtain the H of S, H star from H of S to H star of S. And that residual formula says this. So H star of S, okay, equal a total sign called this residual, okay, of here. So first step, what you do is you rewrite this H of S to, instead of using S, to another symbol. Let's say you call it H of lambda. Okay, so rewrite this H of S, okay, to H of lambda, or you can use another symbol, doesn't matter. So then what you do is you multiply this H of lambda with this, okay, with this. So this is 1 over 1 minus e to the power negative capital T bracket S minus lambda. Okay. So that's H of lambda multiply this. Okay. So what we're trying to find is, the residues of this one at where? At the poles. Okay. Lambda equal to lambda 1 of H of lambda. Okay. Of H of lambda. Now you might be wondering what exactly this residual means, right? Yeah. So residual is a term. However, you actually have dealt with this concept of residual already. Now remember when you do partial fraction expansion, right? When you do partial fraction expansion, you know, you have this you have, so basically when you do partial expansion, let's say z minus minus 1, z minus 2, let's see over z like this. So what do? You say a and b like this, right? Set it like this, partial fraction expansion. So that a and a b basically is called residual. Okay, residual you can term is called residual there, right? Yeah. So back to this formula here. So what we're trying to find is we're trying to find the residuals of this block here, okay, of this one. At where? At this lambda equal to this right here. So here's this formula now. So suppose that you have a number of poles here. So what you do is, right, you will have, if you have m number of poles, you will have m number of residuals here. All right, yeah. If they're all distinct, okay, this is what you can make use of this here. So here's a formula for key 1 to key n. So the key I, so let's see, for distinct real poles. So mostly, well, I'll just try and ask you to practice this one here, okay? Yeah, lambda I. Okay. Then that formula is key I equal to lambda minus lambda I, then multiply by this big block, and then you set lambda equal to lambda I. Okay, so that's how you find the key I there. Okay, that's the residual. Okay, that's residual. If you have not just a distinct, but if you have a repeated poles, there's another formula. Take a look at this lecture notes on that formula. Okay, it's a bit of a long expression, so I'm going to skip that. Okay, so for repeated ones, look at lecture notes. Okay, look at lecture notes. But I'll give you a very simple example right here to illustrate this formula. All right, illustrate this formula. So let's say I have an h of s, which is 1 over s plus 1 and s plus 2. Okay, let's see, this is h of s here. Yes? No. See, I'll show you what happens here. You'll see that it doesn't go to 0. Okay? Yeah, I'll show you what happens. Okay, so let's say if this is my h of s here, right? So what do we do first? We write that using lambda. Okay, is that good? Yeah. So then we apply the formula here now. So if you look at this h of lambda, what do we have? We have 2 poles here, right? We have 2 distinct real poles here. Okay, one is -1, the other is -2. Okay, so if I use my residual formula at here, okay, so what we're going to do is we're going to basically do this step here now. Okay, so we're going to try to find this expression here. So that's lambda plus 1. So let's call this is K1 here. K1 is the residual corresponding to which pole? So corresponding to the pole of lambda equal to -1, right? Okay, so lambda plus 1 multiplied by h of lambda multiplied by the e to the power of -t s minus lambda, right? Then what do? We set the lambda equal to -1. You see, it's not 0 because why? Because this cancel this first. Okay, yeah. It's a very similar like the formula you use to find the a and the b value when you do partial fraction expansion, right? Yeah, very similar. Okay, yeah. So you cancel this first before you apply the lambda equal to -1. So then you apply lambda equal to -1 into here. So what do we get? We get -1 here is 1. So then this is just one chunk at here. 1 minus e negative t s minus -1, so it becomes s plus 1 here, right? S plus 1. Okay? Yeah. Is that good? Yeah. So that's h star of s. So basically, well, that's not h star of s there yet, right? That's basically the h star of s according to the formula equal to k1 and plus the next one, k2, right? K2 is the one corresponding to the pole at lambda equal to -2. So the next step, what you do is you're gonna basically replace that s with 1 over t ln z, right? 1 over t ln z. To obtain what? To obtain this h of z, right? To obtain h of z. Okay? Is that clear? Yeah. So now let's look at, I'm not going to calculate K2, just look at the K1 here. So let's say look at this term here. What happened when I replace the s with 1 over t ln z into here, right? Yeah. So here is K1 here. Yeah, this is K1 here. Okay. So let's see. Well, what are we going to have? Before you do this replacement, it might be a good idea is you rewrite that expression just slightly there, all right? So this is 1 over 1 minus, so this is negative ts plus 1, so rewrite it as this, okay? Was that right? Yeah. And by the way, e to the power of a plus b equal to e to the power of a multiplied by e to the power of b. So if you recall in the second year, so many mistakes, right? I have to mention that. Okay, so this is a constant, so we don't have to do anything here. But if I replace the s with this quantity into here, so let's say e negative ts 1 over t ln z for the s, okay, for the s there. So well, you'll cancel this t first, right? You'll cancel this t first. Okay, now, and what does that equal to? That equal to e negative ln z, right? E to the power negative ln z. And what is e to the power negative ln z? Minus z? It's the answer to the negative, exactly, yeah. Okay, so this negative ln z is ln z to the power -1, so that's z. So this big guy here becomes 1 minus, okay, like this, yeah. So you have the z shows up, right, explicitly. Okay, yeah. That's how you use this residual formula. Okay, when you choose to go this approach here from hss to h star of s, and then from h star of s to h of z. Okay, and if you choose to go from this to this approach here, basically, I know I have an impulse sampler there, and I'm gonna just simply do this z transform. So what would you do is you're going to have to make use of table. Yeah, I have to make use of table. Is that clear? So that's the two approaches that you might use, okay, for discretizing a continuous system. But either way, you might want to use MATLAB in the end to simplify everything or to verify your calculation. So here's the using MATLAB. There's a command in MATLAB called the C2D. Okay, so the continuous to discrete. Okay, you can type help and look at the parameters of the C2D. But in general, what you do for the C2D is you have to define the system first. So this is, you look like we have this first. Okay, give a sampling time, let's say 1 second, and then for any system, C2D is converting the continuous to discrete, right? Converting the continuous to discrete. So you're going to have to define the continuous system first. So let's say coming back here, my continuous system here is this g of s here, right? G of s. So in my example, g of s is 1 over s plus 1. That's my continuous system. That's the numerator divided by denominator. So how you define that continuous system is you define a continuous system by using the numerator denominator. Let's say you call the numerator is, right, it's this way. So the numerator, this is numerator here, right? 1 over s plus 1. So you consider them as a polynomial. You use the coefficient of that polynomial to represent this the system. For example, the numerator here's a typical here. So an sn plus an minus 1 sn minus 1 up to a naught. That's a polynomial, okay? And the coefficient of the polynomial is a naught of this. So in this one here, there's nothing else but just a 1, so which is a naught. So what you do is just 1 in it here, okay? Just a 1. Okay? But the denominator, okay, here's s 1. So then the coefficient, right? So it's going to be what? 1 1. Okay, is that good? Yeah.
It just 1 1.
Yeah.
It's like numbered by.
That's the coefficients here. Say coefficients. Coefficient for s.
No one above. For the numerator.
Yeah. Just 1.
Okay.
Yeah. Okay. So then you define your continuous system as this. So you see the g of s equal using the function called TF, transfer function, right? You learned this in your control system. So just TF, numerator and denominator. Okay. If you want to save yourself a few lines of code, you can just directly put this one here, put this one here. That's okay, right? That's okay. Yeah. And then the next step is to use the C2D now. Now remember what the purpose of this one here. Okay. The purpose is here is a zero order hold. Here is a g of s. Okay. The purpose is to obtain the Z transform of this multiplied by this, right? Yeah, the purpose of this. Now, if you look at this one here, I haven't specified anything about this 0h here yet, right? I didn't specify this. So there are two ways of doing this, two ways to obtain the Z transform. One way is, in the next step, when you use this, so let's say I call this is g of z here, okay? Maybe I should call this. Yeah, okay, let's just say I call this g of z here, okay? This block. Ultimately, I want to obtain a g of z corresponding to the two blocks here. So gz will be using a C2D, okay? So you plug the g of s here, okay? Then plug in the sampling time, all right? Now this is the key points next, okay? This is the key point. Next, okay, you have to specify, okay, what parameter here. So you see there's a zero order hold here, so what you do is 0h, okay? Plug in the 0h. So when you plug in the 0h, the MATLAB knows, oh, okay, there is a zero order hold in front of this g of s. So it's going to do this continuous to discrete by inserting a block in front of here and then do this converting, okay, to this conversion. Is that okay? Okay, so if you do this, you'll get which one is that? You'll get this one. Okay, you get this. Okay, yeah. Now there's another way doing that. So basically, the thing is, if I don't want to do this, okay, if I want to express directly, this is one method here. Okay. Okay, this is one method. So if you want to do the other way is this. Let's say I wanted to define the zero order hold. So let's say I'm not sure you can call 0h in MATLAB, but let's say I'm going to define this zero order hold here, okay? So how do you define this zero order hold? You're going to define the zero order hold using transfer function again, okay? Using transfer function. Where is the zero order hold? It's here, right? It's here, okay? It's here. So you can define your zero order hold using a transfer function here. Yeah, the only question is in zero times you can't express a numerator here, right? You can express a numerator. So what you do is you can use a symbolic things to do that. Basically, you can use a TF. Maybe use this one here. Okay. So S equal to this, then the 0h, just use a symbolic, and then that become 1 negative TS. So just typing this one here divided by S. Okay, just typing this. Okay, so it's typing this. It's not an e to this. I think it's a exp bracket negative t multiplied by s. Right, typing that. Okay, and then you multiply your GS. You multiply the GS with 0h. Okay, multiply the GH with 0h. Okay, let's say you call it another one here. Let's say you call it GH, doesn't matter, whatever you want to call it. Okay, you multiply the two things. Okay, yeah, and then you use your C to D. Okay, so the C to D to this GH at here, and TS. Okay, TS. Actually, that T is TS here. Okay, it's a time sampling time. This is sampling time. Okay, so when you program, make sure everything consistent. So now, instead of specifying a zero order hold now, so this time you're gonna specify it what? IMP. Okay, IMP, impulse. Because right now, what this step here, okay, for this step, okay, for this second method, for this step, you specifically write this block multiplied by this block, right? So now there's no zero order hold in front of this. What's in front of here? It's that impulse sampler, right? Impulse sampler. So that's what you tell the MATLAB. Okay. In front of this GH, there is an impulse sampler, not a zero order hold. Okay. So you're supposed to get the same results. Okay, you're supposed to get the same results. Was that good? Yeah. So try it out and see if that works. Okay. Yeah. If it doesn't work, then debug it. So it's always. Okay. So. Sorry. Who said it? Yeah.
The zero revolt. It's defined already in MATLAB, isn't it? Or you have to define it.
Oh, you mean is there a defined block in defined function for zero order hold in MATLAB? I don't know. Yeah, MATLAB knows zero hold, but so this is what C2D at here will do, right? If you specify the zero hold here, the MATLAB will do it for you, basically. Yeah, which actually generally I recommend you use it. If there's a zero hold, you don't have to go through the second method here. But when I show the second method here, I think what my purpose is, let's say if I give you a generally just S function, right? Just h of s here, right? Just h of s. And you got to be careful is, what are you doing with this h of s here? Are you just simply taking this Z transform of this? Or maybe this h of s is a part of the system, there's a zero order hold in front of this zero h of s, right? So when you take the Z transform, and when you apply this C2D, so you got to be careful is what are you dealing with at here, or what purpose are you?
It's just a part of the system. Then the second method is right?
If it's a part of the system, zero order hold is part of the system, you mean?
Yeah.
Not necessary. Not necessary. Actually, if zero order hold is a part of the system, I recommend using this one here. Yeah. So it saves you time and saves you a couple of lines of code, right? Yeah. So basically, if you look at this table here, okay, if you look at this table here, right, this table. Now the question is, where are they from, right? Can you verify the results at here using the C2D command? Okay, so if I want you to verify using C2D command, basically here is this S function here, right? So you're gonna have to define the S function first, then give it to the C2D, and give it to a certain sampling time. And then, what would you do with this parameter? Would you use the ZOH or would you use IMP? So here's the question. This is actually the key point I want to make here. For this table, right? Let me repeat the question here. If I want you to verify if this table is right or not, I want you to verify using C2D command. So according to the C2D, you had to define the continuous block here, right? Continuous S function first. Then you give that to the C2D, define the T of S, and you have to specify the IMP or 0H or IMP first. So for this case here, you'll see that you have to give this IMP, okay, to get the same results here. Yeah. Why is that? You see the process here. Where's this Z transform from? It's directly by doing what? By the sampling of which one? By doing the sampling of each one of this time function, right? Doing the sampling is the process what we call you have an impulse sampler, right? Impulse sampler in front of this block here. Okay, yeah. Is that clear? Yeah. So for this table here, it's the IMP. Okay. So basically, when you see this, when you see Z, you know, basically when you see Z H of S, I think I mentioned this here. So when you see this, okay, you see forming the Z transform of a certain H of S, okay, writing like this. And that means if you want to verify that using command C2D, you give the option input here as IMP. Okay, IMP. Now the only catch is, but later when you come to the actual system, you know, there's a zero to hold there, and you're not just taking Z of H of S. Okay, you're actually probably taking Z zero to hold plus that H of S. Okay, is that good? Yeah. Try it out and get some ideas, get some impressions about this formula C2D. All right? Yeah. Okay, so let's talk about the next one, open loop pulse transfer function. So actually, we sort of covered this already here, open loop PTF. Okay, because if you look at this example I give you at here, if we look at this example at here, that's an open loop, right? That's open loop, and open loop pulse transfer function. This is kind of the process of obtaining the open loop transfer function. All right? Yeah. Now, I think I just want to cover one example here, which actually I think I sort of mentioned that. Here is an open loop system. Okay, here's open loop system. So the difference, right? The difference is instead of directly connecting the two S function, there is another sampler in between, right? There's another sampler in between. Okay? Yeah. So if we wanted to obtain the pulse transfer function of this system, okay, okay, in order to compare the difference between this system and this system, right? This system. So my whole point here is there's a slight difference now. Okay, actually not slight, it's totally different. For this system, if you combine them together, that's exactly what happens in the previous example, right? Exactly what happened in the previous example. And for this particular one here, if you wanted to go over the process, okay, so this is what happens here. Okay. Anything after the sampler is a starred one. Okay. Let's call this, give a few symbols here. Okay. Okay. Starred one. And the Z transform is always between the ratio of the two star ones, right? It's always between the ratio of two star ones. Okay. So let's say in my particular case, okay, I'll look at this block first. The U of S, so here U of S equal to this X star of S here, and G of S, right? G of S. And this block here, the Y of S equal to this guy here, u star of s multiplied by h of s, right? That's purely based on the block here, okay? Based on block. Then you take the start operation. Remember in the previous lecture, this is start Laplace, okay, transform. So you take the start Laplace transform of both sides here, okay? So that gives us a u star equal to x star and g star. Here we get y star, u star, h star. Okay, h star. Okay, yeah. So in other words, the y star, right, plugging this one over here, okay, over here. So the y star will equal x star of s, g star of s, and then h star of s. Okay, like this. Okay. So the z transform is the ratio between y star and x star, and y star. So at this step here, because everything is a star one now, right? Everything's starred. So what you can do is you can replace the s with 1 over t ln z. Okay, you can replace that. So that basically will give you this yz at here, and xz, gz, and h of z, right? Will give you this. And the ratio between y of z and over x of z is the transfer function. So that gives you this gz, hz. Okay, gz, hz. Okay, so that's the former proof is this, but you don't have to, every time you don't have to go over this. You can remember this one here. Okay. So this is the z transform when you have a sampler between two blocks. Okay, and also there's another one in front of the first block, like this. Okay, was that good? Yeah. So compared to this second case here, the z transform of this is actually what? So you have to multiply these two together first, right? Multiply them together first. Then take z transform of the resulted multiplication results, and then gh. So this is the difference here. Okay, this is the difference. Okay, yeah. So regarding this open loop, that's it. That's basically everything about open loop. Okay, yeah. And the key point is actually going to be the closed loop one here. But let me go over another example here, okay, and I'll show you a couple of commands you can do a simulation, okay, using MATLAB. So let's take an example, and this is more or less of a concrete, let's see, sort of an from an implementation point of view. So suppose you have a digital control system and it's open loop, okay. Okay, so this is open loop 1, or maybe this is just part of the closed loop. Okay, just part of the closed loop. And what happens is you feed in a certain signal into this analog to digital. Then the analog digital, the digital signal give it to a so-called digital filter, and the digital filter basically the digital controller right here. Okay, the digital controller. And the output of digital controller given to a digital to analog converter, then the resulted value given to the plant. Okay, so that's a sort of open loop digital control system. Okay. Okay, so when you see this kind of system, and if we're trying to obtain an open loop pulse transfer function for this system here, so what we need to do is we need to basically figure out what each block does, right? And what will be the mathematical model for each block. All right, yeah. This A to D, it's more or less, actually you don't really need to know, it's more or less of a sampler there. Basically, it gives us a discrete signal out of this A to D, right? Discrete signal. So this is more or less a sampler, okay? Yeah. And the digital filter is the controller, okay? So this is basically usually represented by a difference equation, if you recall that, okay? Or you can use a Z block, because this is already discrete. So you can use a Z block to represent this digital filter. And what's coming out of the digital filter, okay, is still a discrete signal. The discrete signal is the digital ones given to a digital to analog signal block. So that block does is it's going to convert to analog ones. It actually usually it does not just convert to analog. It also contain this block here. Usually also contain a zero order hold. Okay, yeah. So over here there is a zero order hold, okay, included usually. Okay, so when you see a DA, so that means they generally will have a zero order hold included. Maybe there's higher order, but in our case we'll just consider zero order hold. Okay, yeah. And then give it to this GPS here, right? GPS. Okay. Yeah. So let's see what's come out of here is, okay, as a continuous m of t, not a continuous time signal, m of t at here. Okay. So after zero order hold is this. Okay. So then in general, what happens is for this d of z, right? So you can see now the m of z will equal to d of z multiplied by e of z, right? Multiplied by e of z. Okay. Yeah. And this m of t at here, right? This m of t and the corresponding one's m star of s here. Hang on a sec, as no, sorry. What I'm talking about here. Yeah. So the m of kt at here corresponding to m star of s at here, right? M star of s. Okay. Yeah. Then the block here has a zero order hold. The block here has a zero order hold. Then that's m. Okay. Over here, let's say m of s there will equal to the zero order hold multiplied by this. And zero order hold is, right? It's this one here. Okay. Then multiplied by what's coming out here. All right. Yeah. Coming here. So then overall, if your output here is a C of S, let's say this is my output here. Okay. Say CT. Okay. This is my output. Okay. Then the CT or C of S, or the C of S equal to the signal at here multiplied by this plant, right? Multiplied by this plant. The signal there is m of s multiplied by the plant. Okay, multiplied by the plant. Okay. Then plugging this one here, so that's 1 ETS over s, m star of s, and GP of s. Okay, GP of s. Okay, yeah. So maybe I'll write just slightly here. I'll move this GP of s to the front, and m star of s at here. Okay, star of s here. So now these two can be combined into one block at here if you know the plant, right? If you know the plant. Okay. So then you take the start operation, start Laplace transform. So C star equal to the start of here. Let's see, I would call this G of s. So that's G star of s. Okay, m star of s. Okay, G star of m star of s. So in other words, you can now convert s into the z now. Okay, we convert into the z. Okay, into the z. And what's m of z? M of z is over here. dz, ez. So that way you can have, okay, you have this. Okay, you have this. Okay, so the pulse transfer function is between the input output, and that's g of z and dz. Okay, g of z, dz. Okay, that's it. That's the pulse transfer function for that block. It basically consists the multiplication of two things. One's the digital controller, and the other is a discretized plant. You see this GZ? What's the GZ? Is this, right? It's this. Okay, it's this. So that's the discretized plant. So in a short diagram, okay, so this is actually the previous block can be redrawn like this. Okay, so it's equivalently like this plot here, right? Equivalent like this, right? So d of z here, zero order hold, and GP of s, the corresponding open loop pulse transfer function, it's this. Okay, it's this. It's all good? Yeah? Okay. So the next thing is I want you to practice, okay? I want you to practice using MATLAB, but I'll just give you this example here to practice the few ways of doing simulation. But number one is do some kind of a hand calculation. Let's say based on this example here, okay? The d of z, okay, is described by a difference equation. Okay, if the d of z is described by this difference equation, I'm not exactly sure what this is, but just in general, okay? Yeah. So then, let's say based on the difference equation, what would be the d of z? So what would you do? You basically take a z transform on both sides of this equation here, and that's give you m of z. Z transform this give you e of z, and z transform this. There's one delay, so what does that give us? Right. Just z negative 1 e of z. Okay? And the ratio give us d of z. So the ratio, which is 2 minus this, or 2z minus 1 over z. Okay? Yeah. So that's the d of z. And let's say my GP of s, okay, suppose my plant, just like in the previous example, it's 1 over s plus 1. Okay, if this is plant here, okay, so this is plant. Then, according to the pulse transfer function, let's see what will be the results, okay, for this open loop. Okay, so then, if this is the plant here, this is the plant, and what we need to do is we need to find the z transform of these two blocks first, right? Of these two blocks. Okay. So z transform of this zero order hold. So let's call this is g of s right here. So g of s, right? G of s. And you can do that. I think we obtained in the previous example, which is, right? We obtained from previous example, which is this guy. Okay, in the previous example. So the next step is to multiply this and together with that to obtain the open loop pulse transfer function. So then your open loop pulse transfer function is this multiplied by this. Okay, yeah. And that gives us this. That's it. That's the hand calculated pulse transfer function, right? Pulse transfer function. Okay. Then the question is, you want to look at the response of the system, right? Here's open loop, and I really want to know how the system will respond to a different input, or what will be the stability of the system. And in order to test the stability of the system, there are two responses that we're very interested in. One is what? One is called the step response. The other is called impulse response, right? So basically, this E of Z is input here. If I wanted to check out the step response, it essentially means I'm going to give the input a step input. If it's a step input, what is the Laplace transform? Oh, sorry. What's the Z transform of this step input? It's this, right? It's this. Okay. So you basically plug in this one here. Okay. Plug in this. And then if this is the input here, then the output will be simply C of Z equal to this multiplied by E of Z, right? Okay, so that's the output. Okay, that's the output. Of course, this doesn't really tell you anything because it's hard to see, right? You need to look at it to see what happens. But I'll just write down in general. If we're looking at the impulse response, then the E of Z will basically equal to 1, right? Equal to 1. Okay. Yeah. So in other words, your impulse response is just inverse Z transform of this chunk right here. Okay, of this chunk. Okay. So that's how you're going to conduct the simulation. Or if you do hand calculation, you basically wanted to know what the C of k is. You want to take the inverse transform of this corresponding C of Z. Okay, and to look at the response here, right? That's hand calculation. Was that good? Yeah. Okay. But there's a quick way of doing this, though. Okay, let me write this one here. Let's see. Take a look at the step response. So if I take a step response, what's my step response? Step response is it's this block multiplied by this block. So what do we have? We have 1 minus this. So this Z cancelled that Z, right? Okay, that's C of Z. Okay, this is C of Z. And if you take Z transform, find the C of k, you'll find a response. Now, there's a quick way is to use that so-called the final value theorem. Final value theorem, right? Remember, the final value theorem is to check what is the C infinite. Basically, when k goes to infinite, what's the value of that, right? Of the value. And the formula is, look at the table. Okay, it's this. Okay, it's this multiplied by that. Okay, here's a one mistake in
the limit is that approaching 1.
Yes, that to 1. Okay, yeah. So let's say if I do this, you can very easily get this 1 minus Z to the power 1 is Z over Z, Z minus 1 over Z. So you cancel 1 of Z minus 1 here. Okay, cancel 1 of that. So the Z minus 1 is cancelled. There is a Z at here. Okay. Yeah. Was that okay? Yeah. So then you plug in, basically you let Z go to 1, right? Let Z go to 1. In this case, just let Z go to 1. So Z equal to 1 here, this is 1. Z equal to 1 here, this is 1. Z equal to 1. So 1 minus this cancel each other. So this is equal to 1, right? Equal to 1. Okay. So basically, the step response is supposed to settle down at 1, right? Settle down at 1. Okay. Yeah. Okay. So that's purely mathematical derivations, and there's no simulation yet, right? And I want you to do some simulation, to run some code for this simple system. Then you can build upon it for more complex system later. All right? Yeah. I tried 2 different ways of doing this simulation. Okay. One way is the code given in the lecture notes, right? On the page 6, I believe. So Let me open up the lecture notes in here. And there's an by the way, the lecture notes are kind of updated on the fly. So usually you should download the latest version after the class, a couple of days. For example, I just updated last night. So the one uploaded on Monday is actually an older version. This is actually an older version, and in my other computer is a good one. But anyway, so this is one we were doing this one here, okay? There in MATLAB, there are really different kind of function. So if you have the toolbox, you can use the function. If you don't have the toolbox, you might not be able to use the function. So the filter, I believe the filter is a digital filter toolbox. Maybe it's not a general here, but try it out first. All right? Yeah. So this is one way of doing the simulation. In this simulation approach here, that heavily relies on the derivation of the final results. So this is the final results of step in this is let's see, hang on a second here, okay? X, yeah, numerator. This is I define a numerator here. So this numerator, what's the numerator? That multiplied by, this is 1 minus e to the power of negative t multiplied by 2z minus 1 here, right? Can you see this? Do you know how, have you used the command conv here, convoluting basically? No? Yeah. So that command there, okay, so you see this one here, right? This 1 minus this. Okay, so how do I get this one here is for this one here it's a block of just 1 minus this. For this one here is a 2 negative 1, right? 2 negative 1. So you're supposed to multiply each other. You can use conv, and that give you the results of this multiplication. Okay, yeah, that's what that command is for. The second one here is for the denominator. Okay, for the denominator. So conv, this is a z, and this is another one. Here. Denominator makes sense here. Just a second here. Oh yeah. So this is a second one here, right? This is the PTF here, right? This is a PTF, right? This is PTF. So that command there is just trying to define this pulse transfer function, okay? Pulse transfer function. And numerator, this is the numerator here, right? I'll write down the pulse transfer function. Sorry about this. Okay. You see that, right? This is a PTF here, right? This is a PTF, okay? And the numerator PTF is this, okay? Numerator. Now, what is the denominator of the PTF? Denominator PTF is this multiplied by this, right? Is this. The Z here, so that's the convolution. Yeah, well, not a convolution. It's a convolute process in the MATLAB. The Z here, it's 1, 0, right? Z is 1, 0. And this z minus e to the power of negative t is what? It's 1 negative the exp negative t. See that? Is that good? So that's what this code here, right? This is not 1 minus this. There are two things. One, and the other one's negative exp bracket negative t. Okay? Yeah. So that's the numerator denominator. Okay? That's how you define the pulse transfer function. Okay. Then you do the simulation based on this pulse transfer function. If we are doing step input, right? We're doing step input. It basically means we're gonna multiply this transfer function with the step input, right? With the step input. So the way to define a step input here is it's sort of a dummy way. Is I defined a number of a sequence of ones. Basically step input is all one, right? Yeah, and then give it to the filter command. When you give it to the filter command, the first parameter for the filter is the numerator of the pulse trans function. The second one is the denominator of the pulse trans function. The third one is the input, x. Okay? The output is the response. So that's what the response looks like, right? It reached at 1. Is that clear? Yeah. And in updated the lecture notes, I had a couple of more examples. Instead of using filter, you can also use another command called step z. Okay, you can also use command step z. So that's how you can do that. All right. Yeah. I have also uploaded a MATLAB file, okay, called the Lecture4 example 4 here, and there's another one here using TF, C to D, using multiplication, using step to do the simulation. So check this out, verify this. Okay, so this will be basically something you can build upon for your future work. Okay, any questions? All good? Right.